Dear students, you are all welcome to this lesson about Gauss theorem and its applications. Today, I will start by sharing the learning objectives for this lesson with you.
On completion of this topic, learners will be able to define electric flux, express relation between electric field intensity and electric flux, discuss Gauss's law and its applications, derive an expression for electric field due to line charge, derive an expression for electric field due to an infinite plane sheet of charge, derive an expression for electric field due to two infinite plane parallel sheets of charge.
ਜੀਵਨ ਵਿੱਚ ਕਈ ਵਾਰ ਕਿਸੇ ਸਿਚੁਏਸ਼ਨ ਵਿੱਚ ਨਾ ਕੇਵਲ ਮੈਗਨੀਟਿਊਡ ਸਗੋਂ ਓਰੀਐਂਟੇਸ਼ਨ ਜਾਂ ਡਾਇਰੈਕਸ਼ਨ ਵੀ ਮਹੱਤਵਪੂਰਨ ਹੁੰਦਾ ਹੈ। ਜਿਵੇਂ ਕਿਸੇ ਪਾਣੀ ਦੇ ਸੋਰਸ ਤੋਂ ਪਾਣੀ ਦਾ ਵਹਿਣਾ। ਇੱਥੇ ਯੂਨਿਟ ਟਾਈਮ ਵਿੱਚ ਸੋਰਸ ਵਿੱਚੋਂ ਪਾਣੀ ਦੀ ਕਿੰਨੀ ਮਾਤਰਾ ਵਹਿੰਦੀ ਹੈ ਜਾਂ ਡਿੱਗਦੀ ਹੈ, ਇਹ ਸੋਰਸ ਦੀ ਓਰੀਐਂਟੇਸ਼ਨ ਤੇ ਨਿਰਭਰ ਕਰਦਾ ਹੈ। ਆਓ ਇਸ ਸਥਿਤੀ ਨੂੰ ਵੇਖ ਕੇ ਸਮਝੀਏ।
Consider a dam having a gate fitted with cylindrical pipe. Now, consider that a circular ring is held in a stream of water for measuring the amount of water flowing through it. The amount of water flowing through the ring will depend on the orientation of the ring. If the ring is held normal to the flow of water, the maximum amount of water will flow through the ring and the amount of water flowing will be minimum. Then the ring is held parallel to the water flow.
It is clear that in this situation, the area of the ring is to be treated as a vector. Obviously, the direction of area vector should be along normal to the plane of the area. To tackle this situation mathematically, we will consider an area element ds represented by the vector ds such that the arrow representing the area vector ds is perpendicular to the area element. The length of the area vector ds represents the magnitude of the area element ds. In case vector n cap is a unit vector along normal to the area element ds, then vector ds is equal to ds into unit vector n. Conventionally, the area vector representing an area element of a closed surface enclosing a volume in assigned direction such that the area vector is directed along the normal pointing outwards from the closed surface. To be able to understand Gauss' law, it requires defining a new term called the electric flux. Well, the term is related to electric field, of course. Let's see what is electric flux. If a surface S be placed inside an electric field vector E, then the electric flux through a surface held inside an electric field represents the total number of electric lines of force crossing the surface in a direction normal to the surface. Electric flux is a scalar quantity and is denoted by phi, which is associated with electric field. Now, let's see the relation between electric field intensity and electric flux.
A surface S is placed inside an electric field of intensity vector E. The electric lines of force crossing the surface S in a direction normal to it. For measuring the electric flux through surface S, consider a small area element ds of the surface S represented by vector ds, which is directed along normal to the area element ds. As the surface starts rotating about its edge, its elementary part also starts rotating. Let at any instant area vector ds make an angle theta with the electric field vector E. Thus, ds cos theta is along the electric lines of force.
The electric flux through a planar area is defined as the electric field times the component of the area parallel to the field. Thus, the component of electric field along normal to the area element ds means that along area vector ds is given by En equal to E cos theta. Hence, electric flux crossing the area element ds in a direction along normal to it is given by d phi equal to En into ds, which is equal to E cos theta into ds. As here the electric field is not perpendicular, therefore, at this moment the electric flux crossing the area element ds in a direction along normal to it is the product of electric field E and ds cos theta. That is, d phi is equal to E into ds cos theta. The electric flux through area vector ds can be represented in vector notation as d phi equal to vector E dot vector ds. Let this be equation 1. The electric flux through the whole surface S can be found by integrating equation 1 over the whole surface S. Therefore, total electric flux through the surface S is given by phi equal to integration of vector E dot vector ds over a surface S, which is equal to integration of En into ds over a surface S. Thus, electric flux linked with a surface in an electric field may be defined as the surface integral of the electric field over that surface. The electric flux through a closed surface is denoted by capital phi. Thus, if the surface S is a closed surface, then the total electric flux through the closed surface S is given by capital phi equal to surface integral of vector E dot vector ds over a closed surface S, which is equal to surface integral of En into ds over the closed surface S. The SI unit of electric flux is Newton meter square per coulomb. If you have understood the concept of electric flux, it will be easy for you to understand the Gauss law. Gauss law ਉਹਨਾਂ physical laws ਵਿੱਚੋਂ ਇੱਕ ਹੈ ਜੋ ਕਿ ਬਾਉਂਡਰੀ ਦੀਆਂ ਪ੍ਰੋਪਰਟੀਜ਼ ਅਤੇ ਉਸ ਰੀਜਨ ਦੇ ਇੰਟੀਰੀਅਰ ਵਿੱਚ ਕਨੈਕਸ਼ਨ ਬਣਾਉਂਦਾ ਹੈ। Gauss law ਵਿਸ਼ੇਸ਼ ਤੌਰ ਤੇ closed surface ਵਿੱਚ ਚਾਰਜ ਅਤੇ ਉਸ ਸਰਫੇਸ ਵਿੱਚੋਂ net electric flux ਨੂੰ ਰਿਲੇਟ ਕਰਦਾ ਹੈ। Gauss law states that the total electric flux over a closed surface equals the total charge enclosed by that surface divided by a constant. Now, if Q is the total charge enclosed by a closed surface S, then the total electric flux over the closed surface S is capital phi equal to Q by K. In vacuum, this constant K is called the electrical permittivity of free space and is denoted by the Greek letter K is equal to epsilon naught. Thus, we have capital phi equal to Q by epsilon naught. By definition, the total electric flux through the closed surface S is given by capital phi equal to surface integral of vector E dot vector ds over the closed surface S, where Vector E is the electric field at the area element vector ds. Thus, Gauss law can be expressed as surface integral of vector E dot vector ds over a closed surface S equal to q by epsilon naught. Hence, we can restate Gauss law as if a closed surface encloses a charge, then surface integral of the electric field due to the enclosed charge over the closed surface is equal to 1 by epsilon naught times the charge enclosed. ਤੁਸੀਂ ਜਾਣਦੇ ਹੋ ਕਿ ਸਿੰਪਲ ਕੇਸਿਸ ਵਿੱਚ ਇਲੈਕਟ੍ਰਿਕ ਫੀਲਡ ਇੰਟੈਂਸਿਟੀ ਦੀ ਕੈਲਕੂਲੇਸ਼ਨ ਕੂਲਮਸ ਲਾਅ ਯੂਜ਼ ਕਰਕੇ ਕੀਤੀ ਜਾ ਸਕਦੀ ਹੈ। ਕੁਝ ਅਜਿਹੀਆਂ ਸਿਚੁਏਸ਼ਨਸ ਵੀ ਹਨ ਜਿਨ੍ਹਾਂ ਵਿੱਚ ਕੂਲਮਸ ਲਾਅ ਜਾਂ ਪ੍ਰਿੰਸੀਪਲ ਆਫ ਸੁਪਰਪੋਜੀਸ਼ਨ ਅਪਲਾਈ ਨਹੀਂ ਹੋ ਸਕਦਾ। ਹਾਂ, ਇੱਥੇ ਇਲੈਕਟ੍ਰਿਕ ਫੀਲਡ ਗੌਸ ਲਾਅ ਰਾਹੀਂ ਕੈਲਕੂਲੇਟ ਕੀਤੀ ਜਾ ਸਕਦੀ ਹੈ। If the electric field is not constant, determining the electric flux using integration becomes very tedious. For evaluating the surface integral, we have to choose a closed surface enclosing the charge distribution. The surface so chosen is called the Gaussian surface. Gaussian surface ਤੇ charge distribution ਭਾਵੇਂ point charge ਹੋਵੇ ਜਾਂ line charge ਜਾਂ surface charge ਜਾਂ volume charge ਹੋਵੇ, ਇਹ closed surface ਹੀ ਹੋਵੇਗਾ ਤਾਂ ਕਿ surface ਦੇ ਹਰ point ਤੇ electric field ਦੀ intensity ਇੱਕ ਸਮਾਨ ਹੋਵੇ ਅਤੇ electric flux surface ਤੇ normal ਦੀ direction ਵਿੱਚ ਹੋਵੇ। Thus, Gauss law can provide a useful tool to calculate electric fields from various charge distributions. ਲਓ ਫਿਰ ਹੁਣ ਅਸੀਂ Gauss law ਦੀਆਂ ਕੁਝ ਹੋਰ applications ਬਾਰੇ ਜਾਣਦੇ ਹਾਂ। We will first examine the electric field due to a continuous line of charge on a line segment of length L.
Consider a thin, infinitely long straight line charge of length L having a uniform linear charge density lambda placed along y-axis. By symmetry, it follows that electric field due to line charge at a distance r in any plane at right angles to the line charge is of the same magnitude and is directed radially outward. To find electric field due to line charge at point P, distant r from it, consider a cylindrical surface of radius r and length L about the line charge as its axis. This cylindrical surface may be treated as the Gaussian surface for the line charge.
Let us now calculate the electric flux that crosses the Gaussian surface from the charge enclosed by the Gaussian surface. Since electric lines of force are parallel to end faces or the circular caps of the cylinder, there is no component of the field along the normal to the end faces. The electric flux crosses only through the curved surface of the cylinder as the electric field due to the line charge is normal to the curved surface. If E be the magnitude of electric field at point P, then electric flux through the Gaussian surface is given by capital phi equal to electric field E into area of the curved surface of a cylinder of radius r and length L, or capital phi equal to E into 2 pi RL. Since according to Gauss theorem, capital phi is equal to q by epsilon naught. Since the linear charge density is lambda equal to q by L, which implies q is equal to lambda into L, where q is the charge enclosed by the Gaussian surface. Therefore, we have capital Phi equal to lambda into L by epsilon naught. Comparing the two equations, capital Phi equal to E into 2 into pi into RL and capital Phi is equal to lambda into L by epsilon naught. For phi, we get E into 2 into pi into RL equal to lambda into L by epsilon naught. Simplifying this, we get E is equal to 1 by 2 pi epsilon naught into lambda by R. In contrast to electric field due to a point charge, which decreases inversely as the square of the distance from the charge, the field due to a line charge falls off as 1 by R. Let us now learn to calculate the electric field due to an infinite plane sheet of charge.
Consider an infinite thin plane sheet with positive charge having a uniform surface charge density sigma on both sides of the sheet. Due to the symmetry of the sheet, the electric field is perpendicular to the plane sheet of charge and is directed outwards. For finding electric field due to the plane sheet of charge at any point P, distant r from it, consider a cylinder of cross-section area A as the Gaussian surface passing through the point P. Here, electric lines of force are passing parallel to the curved surface of the cylinder. Hence, the electric flux due to electric field of the plane sheet of charge passes only through the two circular caps of the cylinder. Let Q be the charge enclosed by the Gaussian surface.
Thus, if E be the magnitude of electric field at point P, then electric flux crossing through the Gaussian surface capital Phi is equal to electric field E into area of the end faces, that is the area of the circular caps of the cylinder of radius r, which implies capital Phi equal to E into 2a. As according to Gauss theorem, we have capital Phi equal to Q by epsilon naught. Then the surface charge density sigma is equal to Q by A. That is, the charge enclosed by the Gaussian surface is Q equal to sigma into A. Therefore, capital Phi is equal to sigma into A by epsilon naught. Comparing equations, capital Phi is equal to E into 2a and capital Phi is equal to sigma into A by epsilon naught. For capital Phi, we get E into 2a equal to sigma into A by epsilon naught. On simplification, we get E is equal to sigma by twice epsilon naught. Hence, the magnitude of the electric field at a point due to an infinite plane sheet of charge is independent of its distance from the sheet of charge. And now, we will be learning about the electric field of an infinite plane conductor having finite thickness. As here, Q equal to sigma A is the charge on each side of the plane. Therefore, the Gaussian surface will include a charge Q equal to sigma into 2a. Therefore, we have E into 2a equal to sigma into 2a by epsilon naught. Simplifying this, we get E is equal to sigma by epsilon naught. The next, we will be learning about electric field due to infinite plane parallel sheets of charge.
Consider two infinite plane parallel sheets of charge A and B having surface charge densities equal to sigma A and sigma B respectively. The two sheets divide the space into three regions, namely region 1 lying to the left of sheet A, region 2 between the sheets A and B, and region 3 to the right of sheet B.
Here, in each region, we will find the electric field due to each of these two parallel plates. In the first region, the electric fields due to both the sheets of charge will be from right to left, which is opposite to the direction in which distances are measured as positive. Since electric field due to a sheet of charge is given by E equal to sigma by 2 into epsilon naught, the electric field due to sheets A and B in region I will be E equal to minus sigma A by twice epsilon naught plus minus sigma B by twice epsilon naught, which is equal to minus 1 by twice epsilon naught into whole of sigma A plus sigma B. Electric field in region 2, here the electric field due to sheet of charge A will be from left to right along positive direction, and that due to sheet of charge B will be from right to left along the negative direction. Therefore, in region 2, the electric field due to sheets A and B will be E equal to sigma A by twice epsilon naught plus into minus sigma B by twice epsilon naught, which is equal to 1 by twice epsilon naught into whole of sigma A minus sigma B. Electric field in third region, then in the third region, the electric fields due to both the sheets of charge will be from left to right, that is along positive direction. Therefore, in the third region, the electric field E is equal to sigma A by twice epsilon naught plus sigma B by twice epsilon naught, which is equal to 1 by twice epsilon naught into whole of sigma A plus sigma B. Have you ever thought what will be the electric field due to infinite parallel plane sheets of finite charge if both the sheets have same charge density and have opposite charges? In other words, if sigma A and sigma B are the charge densities of first and second sheets respectively, then sigma A is equal to sigma and sigma B is equal to minus sigma. Now, let's see the electric field of such infinite parallel plane sheets of charge in different regions. Since the electric field due to sheets A and B having charge density sigma A and sigma B in the first region is E equal to minus 1 by 2 epsilon naught whole into sigma A plus sigma B. Now, the electric field due to sheets A and B having charge density sigma and minus sigma in region first is E is equal to minus 1 by 2 epsilon naught into whole of sigma minus sigma, which is equal to 0. As the electric field due to sheets A and B having charge density sigma A and sigma B in the second region is E equal to 1 by 2 epsilon naught into whole of sigma A minus sigma B. Now, the electric field due to sheets A and B having charge density sigma and minus sigma in the second region is E equal to 1 by 2 epsilon naught whole into sigma plus sigma, which is equal to sigma by epsilon naught. As the electric field due to sheets A and B having charge density sigma A and sigma B in the third region is E equal to 1 by 2 epsilon naught into whole of sigma A plus sigma B. Now, the electric field due to sheets A and B having charge density sigma and minus sigma in third region is E equal to 1 by 2 epsilon naught into whole of sigma minus sigma, that is equal to 0. Let us now solve a numerical problem. A spherical Gaussian surface encloses a charge of 9 into 10 raised to the power minus 9 coulomb. Calculate the electric flux through the surface. Since the electric flux through the surface is given by capital Phi equal to Q by epsilon naught. Here we have Q is equal to 9 into 10 raised to the power minus 9 coulomb and epsilon naught is equal to 8.85 into 10 raised to the power minus 12 coulomb square per Newton meter square. Now, substituting the values of Q and epsilon naught in the expression for capital Phi, we get the total flux through the Gaussian surface as capital Phi equal to 9 into 10 raised to the power minus 9 coulomb by 8.85 into 10 raised to the power minus 12 coulomb square per Newton meter square, which is equal to 9 into 10 raised to the power 3 upon 8.85 Newton meter square per coulomb. On simplification, we get the total flux through the Gaussian surface as capital Phi equal to 1.01 into 10 raised to the power 3 Newton meter square per coulomb. Let us take one more problem. Calculate the number of electric lines of force originating from a charge of 6 microcoulomb. We know that the electric flux or total number of electric lines of force passing through the surface is given by capital Phi equal to Q by epsilon naught. We have Q is equal to 6 microcoulomb, which is equal to 6 into 10 raised to the power minus 6 coulomb, and epsilon naught equal to 8.85 into 10 raised to the power minus 12 coulomb square per Newton meter square. Substituting the values of Q and epsilon naught in the expression for capital Phi, we get the total flux through the Gaussian surface as capital Phi equal to 6 into 10 raised to the power minus 6 coulomb by 8.85 into 10 raised to the power minus 12 coulomb square per Newton meter square, which is equal to 60 into 10 raised to the power 5 by 8.85 Newton meter square per coulomb. On simplification, we get the total number of lines of force passing through the Gaussian surface as capital Phi equal to 6.77 into 10 raised to the power 5 Newton meter square per coulomb. We will now summarize all that we have learned today. The electric flux through a surface held inside an electric field represents the total number of electric lines of force crossing the surface in a direction normal to the surface. Gauss' law states that the total electric flux through a closed surface enclosing a charge is equal to 1 by epsilon naught times the total charge enclosed. Electric field due to a continuous line of charge density lambda is E equal to 1 by 2 pi epsilon naught into lambda by r. Electric field due to an infinite plane of charge density sigma is E equal to sigma by 2 into epsilon naught. ਹੁਣ ਅਸੀਂ ਅੱਜ ਦੇ ਟੌਪਿਕ ਦੇ ਅਖੀਰ ਤੇ ਆ ਗਏ ਹਾਂ। ਤੁਹਾਡੇ ਲਈ ਕੁਝ ਸਵਾਲ ਹਨ, ਦੇਖਣਾ ਹੈ ਕਿ ਤੁਸੀਂ ਕਿੰਨਿਆਂ ਦੇ ਜਵਾਬ ਦੇ ਸਕਦੇ ਹੋ। The first question is, what is electric flux? The answer is the electric flux through a surface held inside an electric field represents the total number of electric lines of force crossing the surface in a direction normal to the surface. The next question is, state whether electric flux is a scalar or a vector quantity. You know the answer. Electric flux is a scalar quantity. The last question for today is, does the strength of electric field due to an infinite plane sheet of charge depend upon the distance of the observation point from the sheet of charge? The answer is no. The strength of electric field due to an infinite plane sheet of charge does not depend upon the distance of the observation point from the sheet of charge. I am confident that all of you could answer all the questions. I hope you enjoyed the lesson as much as I did and must be looking forward to the next class. Thank you for your attention and see you next time again.